So I made these really cool dithering shaders. This scene looks like Minecraft, but rendered only with dots. These dots are not placed randomly. It's actually an algorithm that goes through every pixel and decides if it should be black or white. In this video, I will break down and explain the algorithms creating these effects using simple animations. But first, we need to talk about printers. Printers use cartridges that come in 4 different colors: cyan, magenta, yellow, and black. They then place dots of different sizes to create any color in a technique called halftoning. So let's say we have this grayscale pepper. How can we render this with only white and black? This image is made of pixels, so we're not going to use dots of different sizes. We're going to use something called dithering. People that do pixel art like to use very small color palettes. This is to have more cohesive art, and dithering is a technique to make intermediate colors that fill the gaps in the color palette. In the past, retro games had a lot more dithering, especially for transparency. But there's still dithering in modern games, like this effect in Mario Odyssey, and this one in Return of the Obra Dinn. So now, how do we dither our pepper? One idea might be, say, let's take a threshold, and anything lighter than that, let's set it to white. Anything darker, let's set to black. The result is not very good. We can easily improve this by just adding some random noise to the image, so it becomes like this. Now, this is an improvement, but it's far from good. There's actually a ton of different approaches for dithering. To showcase the dithering algorithms, I needed something cool, so I forked this Minecraft clone written in C++ and OpenGL. It was written by some cool guy I ended up corresponding with by email. Now I'm ready to start. I want my effect to be black and white, so I first need to convert the colors to grayscale. This is done by using this weighted average, which looks better to humans than averaging red, green, and blue values. To make sure the points will be visible, I decided to downsample the game and then upsample it again. The first algorithm that I will showcase is called Floyd-Steinberg Dithering. What's nice about this effect is all the points look random, even though they are not actually randomly placed. So let's say we have a grayscale image. Each color value is between 0 and 255. Where 0 is black and 255 is white. To follow the Floyd-Steinberg algorithm, we first look at the top left pixel and see if it's closer to white or to black. In this case, it's closer to black because 92 is closer to 0 than to 255. So we'll put this pixel black. By putting this pixel to 0, I've changed the image by 92. So we will say there's an error of 92 in this image. And the next step of this algorithm is just to propagate this error to the neighboring pixels. So looking at this table with the fractions, which looks complicated but it really isn't, it just tells us what neighbors get what share of the error. So from our 92, the pixel to the right gets 40. That's 92 times 7 over 16. Just to clarify, the asterisk is representing the pixel we just updated, so the one that we decided to set to black. So the pixel to the right of the asterisk is associated with the pixel to the right. So we can take this 98 and add 40 from the table, so now we have 138 here. Then take the bottom 3 of the table and add them up to the 3 below here. And even if one is out of bounds and gets ignored, that's totally fine. So now we can just move to the next pixel, that is the 138, and it's closer to 255 than 0, so we set it to white. This time our error is negative 117. Then we generate the table from the Floyd-Steinberg weights, the fractions. We add them to the neighboring pixels. We just repeat this process for every single pixel in our image, and then we get something that looks like a random dithering pattern, but it's actually totally deterministic. Now you might think that if you went to implement this algorithm, it would look like this nice pattern I showed at the beginning of the video. but in reality, it actually looks like this garbage. Here's the problem. If we look at the monochrome spectrum and run the Floyd-Steinberg algorithm on it, the middle part, which is a huge chunk, is actually not that interesting for a cool effect. And most of the colors that you can find in Minecraft are about here. I'm more interested where the points are sparse, like on the sides. I really like the aesthetics of dark mode, and I really like if there's only a few white points here and there, which is what you saw at the beginning of the video. To achieve what I did is I pushed all the colors to be darker in a technique called gamma correction. If your color space is between 0 and 1, you can transform it by just applying an exponent. If the exponent is bigger than 1, it will darken the image. So this is nicer, but we're not done yet. There's still one more trick to make it even better. Remember the table from Floyd-Steinberg Dithering? These fractions sum up to 1 to diffuse all the error, but nothing prevents me from just multiplying by some coefficient less than 1. The final color spectrum looks like this, and that's how I got the effect in the beginning. But there's one big problem with the Floyd-Steinberg Dithering algorithm. One cool thing about the graphics pipeline is that every pixel can be processed independently. This means that you can run the computation for every pixel in parallel on a graphics card. However, we cannot run the Floyd-Steinberg Dithering algorithm in parallel, and the reason is that every pixel depends on the previous one. For this reason, I implemented another algorithm that I want to talk about. This one can run in parallel, and you can write it in a fragment shader, unlike the previous one. This algorithm is called Bayer dithering. The result is really neat, but it looks a lot less random. Bayer dithering uses a table. I chose a 2x2 table, and because I chose a 2x2 table, I will split the image so that it forms blocks of 2x2 pixels. If we look at this first block, I will compare each entry to its corresponding Bayer matrix value. So 92 here is greater than 0. I'm referring to the 0 here and the 92 there. Since 92 is indeed greater than 0, I will set it to white. Otherwise, I would have set it to black. This is the case for the next pixel, as 98 is not greater than 127, so I set this pixel to black. If I continue with the other values, I get this pattern. Now, I can repeat this process for all the other blocks. You might notice that each pixel's computation is independent, meaning that each pixel doesn't depend on values from other pixels, unlike the Floyd-Steinberg algorithm. So this algorithm can run in parallel and be written in a fragment shader. So let's take a look at the Bayer matrix. I chose a 2x2 and got this effect. However, I can use different sizes. For example, this is what a 4x4 matrix does. And this is what an 8x8 matrix does. Wikipedia has a suggested formula for the values of any matrix provided that the size is a power of 2. So you might wonder why the formula gives exactly these values. Notice that these values correspond to 25% intervals. If we run Bayer dithering on a gradient, we will get this. But you can really put whatever you want in there. If I just use random values, I get something like this. But if I do choose the right set of values, I can get a newspaper halftoning effect by forcing clusters to appear. There was an inconsistency in the explanation earlier because I simplified it. If you want to implement Bayer dithering yourself, look into the resources in the description below. The code of the project is also open source on GitHub, so feel free to check it out, and thanks for watching.